impurities.
Okay. Good morning, everyone. First, I would like to thank the organizer for this wonderful conference. For two reasons. I think we've heard a lot of beautiful science, and also because it gave me my first opportunity to come to India, which has been a very nice experience. So today, I will explain you and show you new results we've obtained with this circuit, which is made of aluminum and silicon. And basically, the idea is to couple a two-level system, a quantum emitter, to some thing we called metamaterial, but people might call it a photonic crystal. And I will show you that it enables us to perform a spectroscopy of what we call quantum impurities. And I will explain you what I have in mind when I say quantum impurities. So before going to science, I thought maybe I could do a little bit of geography. So I'm working in Grenoble, France, which is basically located here, not that far from Switzerland and Italy. France is a small country, so basically it's only 2 hours drive from either Switzerland or Italy. Grenoble is a medium-sized city on a French scale, but compared to Indian size, it's almost a town. It's just a town, basically 500,000 people. So it's in the middle of the mountains, so there are two main interests in Grenoble. First one is ski. I think most of the people are coming to Grenoble to visit our ski resorts. I am very much interested in ski, but I think Grenoble is also very interesting for science. And I think it is one of the biggest microelectronic center in Europe. So basically, for me, as a physicist and experimentalist, it's very nice, because if I need anything, any kind of machine to fabricate my sample, I'm sure that somebody somewhere in Grenoble has the right machine to do that. So this is really helpful for me. All right, so now let me thank the person involved in this work. So this is the team I'm working in. And I would like to thank Sebastien and Javier. They are my two PhD students who did this work. And of course, all the team helped us at one point. Okay, and of course, we could not do anything without strong support from our theory colleagues, Serge Laurent and Nicolas Roch. By the way, if you want to understand more about the theory behind all that, Nicolas has a poster in the foyer. And we also have a very strong collaboration with Isaac Snyman from South Africa. All right, so let me start slowly and give you my own definition of what is a quantum impurity, because I mean the topic of this conference is open quantum system. So I think there are various definitions on how to couple a quantum system to a bath. Let me give you mine. So here I'm taking the simplest system, the two-level system, and I have my bath. I don't make any hypothesis on this bath. I'm only defining a coupling strength, gamma, between this bath and this two-level system. And then to obtain a quantum impurity, I need these very three ingredients. So these very simple ingredients. Of course, I need the impurity. I need many degrees of freedom, and we will come back to what does many means later on. But I think the most important part is that we want to be in what, in our jargon, we call the multimode ultra-strong coupling. But to make a long story short, you can just say that you want the coupling to be similar or on the order of the resonant frequency of your system. So basically, it means that many of the hypotheses we are using usually are breaking down. Let me explain you why we think quantum impurity are interesting. So first, they are often referred to as the hydrogen atom of many-body physics. Basically, if you had classes on quantum many-body physics, usually you start with introducing this 1 degree of freedom coupled to a bath, and in various limits, it's relatively easy to work things out. So I think this is a really simple, but still complex system. The second interest is that actually, even though this is an old problem, and as I told you, sometimes it's even an undergrad problem, there is still a lot of new physics which is not understood. Basically, for this system, people use numerical or analytical methods to find out what is the ground state. And I mean, not all of these main, quantum impurity problems are solved, but many of them, I mean, for many of them now we can find the ground state. But as far as the dynamics is concerned, it is much more complex. And I think, of course, if theorists in the audience disagree, that the dynamics, understanding dynamics of quantum impurities remain in most of the cases an unsolved problem. Last but not least, the question we're asking ourselves is what about the bath? Because usually when people are coupling a quantum system to a bath, they are focusing on the system, which is somehow okay, but I think that in the bath there are many interesting things which are happening. So of course, if the coupling is really strong, you cannot consider your bath as Markovian anymore. You can show that there is entanglement which is building up in your bath. And these are the things we would like to explore. So let me now give you a couple of, I mean, more than a couple, but few examples. If my bath is Fermionics, basically, if you know a little bit about solid-state physics, you know that heavy fermions are very good examples of quantum impurities. Basically, they are lattices of quantum impurities. You find similar stuff in exotic superconductors. You can have a quantum impurity problem in nanostructures as well. For example, if you couple a quantum dot strongly to the electrodes, you will observe Kondo effect, and it was observed in various groups around the world. And even more recently, I think people from cold atoms are also starting to explore this kind of physics. We've heard a few things along this line by Monica on Monday. So basically, they are also trying to put a few different atoms, I mean different spaces in some broader bath of other fermions, and then understand how these blue atoms interact with the red. So all these examples are great, but they all belong to the fermionic bath category. And the one we want to look at is the category of the bosonic bath. So how to understand this quantum impurity when my bath is basically made of photons or phonon? So let me start very slowly and come back to the basics. I think we've seen this system many times during the conference, so I can probably go pretty fast. So you have a two-level system. It is coupled via a coupling constant G to a cavity. This cavity has a decay rate, which is basically kappa, and the decay rate associated to the atom or the two-level system is gamma. So basically, you have one two-level system and one bosonic mode, and if you go in the limit where G is much bigger than the dissipation rates, you enter the so-called strong coupling regime. And basically, if you would do the spectroscopy of this system, so here I'm plotting the frequency, and here this is some tuning knob. In our case, it would be magnetic flux. So the spectroscopy would look like that. When the qubit and the photonic mode are crossing, they're actually interacting, so you observe the famous vacuum Rabi splitting and anti-crossing. Nothing new. So then you can say, okay, I want a bigger bath. I want more degrees of freedom because I want to go towards many-body physics. So what you can think about is to stretch your cavity, which is making sense, and it's probably a good idea, but because you will obtain many modes. You know, you will have all the Fabry-Perot modes of your cavity. It's a dense spectrum, which is fine, but there is a price to pay. Basically, if you do so, your coupling, G, will decrease as well. So you win on the number of modes involved, but you lose on the coupling. So now if you think a bit more about what does many-body interaction means, you can say, okay, I want my two-level system to interact with many modes at once. And here, you can see on this picture that this is not the case. Because if I am plotting something similar to before, so magnetic flux and transition frequency, you see that the atom is going through all these modes, and it anticrosses with all these modes, but only one at once. So basically, you come back to a two-body problem. Even though you have all these nice modes around, locally you are coupled to only one mode. So it's still a two-body problem. So the limit you want to be in is this one. You want the coupling to be similar or bigger than the free spectral range. So basically, when your atom comes, it interacts with many modes at once. It repairs, reshuffles everything. And then I think we can start speaking about many body physics, or at least few body physics. For specialists, this would be a discrete version of the spin boson model in the strong dissipative regime. So basically, the spin boson model on a discrete, with a tight binding model. Okay, so this is the outline of my talk. Basically, I will explain you the recipe we've been following to develop this kind of systems. I will spend a bit more time on this photonic waveguide or metamaterial, if you prefer, because this is really at the heart of our experiments. And finally, I will show you a recent result we obtained when we couple a two-level system to this metamaterial. Okay, so I won't have to explain Circuit-QED again and again. I guess we've heard a lot of talk about that. I think it's a very dynamical field as of today. I mean, we've heard about it mainly along qubits and quantum information processing purposes with Michel. Ash also mentioned that they are really nice if you want to interface them with a nano-electromechanical system. Patrice mentioned that we can interface them with spin assemblies to form hybrid systems. And in Michel's lectures as well, we've learned that recently they were able to perform very nice quantum optics experiments using this circuit. And I think there are various reasons, but I think probably the biggest one is that these atoms, they interact very, very strongly with the matter, with the light. So this is why quantum optics with microwave is very, very proficient these days. So, and of course, this strong coupling, this is the property we want to use in our experiment. So let me review briefly what was done in our field along this line before I go to the system we are developing. So you want to couple to many modes and you want to couple ultra strongly, or you want this interaction to be large. So recently there was a very nice paper from a Japanese group. They could couple a qubit very strongly to a single mode cavity. So they could reach a coupling to a frequency ratio on the order of 1. But in this case, it was only one single cavity. So still a two-body system. Then in Andrew Hauck's group, they used this stretch cavity strategy. So it was, again, a very nice idea, but since, as I explained, the coupling then decreases, so even though they have many modes, they were still in the relatively weak coupling regime, so it's not yet the many-body case. More recently, I think, and this is probably the closest experiment to quantum impurity, people in Waterloo coupled a qubit to a fully open transmission line, so to really a continuum. And they could reach very large coupling, which is really nice, I think. But in their case, if you want, their bath is truly speaking a continuum. And then for us experimentalists, handling an infinite number of degrees of freedom is very difficult. I mean, if you want to probe that with some electronics, you want n to be large, so you have many body effect, but you don't want n to be infinite, because how will you measure that? How will you do the tomography of this system? So this is why we are following a slightly different approach. We want what I think is a mesoscopic bath. So we want the number of modes involved to be large enough so we have many body physics, but small enough so we can still probe the bath in a controlled way. And of course, we want this ultra-strong coupling regime. So what's the recipe? How to go to large ends? So if you ask a microwave engineer how to obtain many harmonic oscillators, the answer will be very easy. You take a piece of coax, you take a piece of transmission line. And the reason has been known for a very long time, because basically you can model a coax as an infinite number of L and C oscillators. So basically, if you cut this coax to a given length, you will obtain many harmonic oscillators, and it's a very easy way to obtain your modes. This kind of description has been even pushed to the quantum regime, and basically it's all the base. I mean, this is the basis of the Caldera-Leggett theory to treat dissipation for a quantum system. You're coupling to an infinite number of LC oscillators. So another important point is that if you're using a piece of coax or a very long transmission line, you can also monitor the bath. You can look at what's happening in there. And this is definitely what we want to do. For example, you can apply voltage or current. You can send photon in and look at what is coming out. So you can really look at the bath and at the quantum system at the same time. This is really important. So now the difficult point for us experimentalists, it is how to crank up the coupling. How will I manage to obtain many modes and also a strong coupling? So I could give you a full quantum treatment of that, but I think there is a very simple semi-classical argument. So let me go with this simple one, and we can come to the quantum case later if you want. Okay, so this is my bath. So this is my piece of transmission line. And then I take the simplest possible superconducting qubit. We've seen that you can do that with a capacitor and a Josephson junction. And now I want to calculate the coupling gamma between this guy here and this qubit. So if I want to do this classically, I replace the Josephson junction by an inductor, LJ, and then I can follow the usual very simple RLC circuit derivation. So if you remember your electronic classes, basically this is like a resistance in series with a C and an L. So you can calculate the resonant frequency of this guy. It's going to be 1 over square root LC. You can calculate the dissipation or the coupling, and it scales as the real part of the impedance divided by 2 LJ. So now if you want to infer this ratio, gamma over omega q, this is what you obtain. So the important point to notice is that this ratio here is not proportional to the impedance of this guy. So if you want to crank up the coupling, you'd better work out a very large impedance. I promised a little bit of quantum, so again, you can go through the full derivation, and this is what you obtain, what you would obtain in the quantum case. So gamma over omega q then is proportional to alpha, which is the fine structure constant. So it's alpha to the 1 because it's a 1D atom. If it would be a 3D atom, it would be alpha to the cube, just for specialists. Now, if you are using atom, maybe you remember that the fine structure constant is 1 divided by 137, so basically 1%. So if you work with atom, you're gonna be in a weak coupling regime. But if you're dealing with circuits, you can demonstrate that alpha is proportional to the ratio between the impedance and the quantum of resistance. Quantum of resistance being on the order of 6.5 kilo ohm. So it means exactly the same than this classical argument I gave before. You need to work hard to obtain an impedance which is as large as possible. And again, if you work with the usual circuits, the impedance is on the order of 50 ohm. And so if you have 50 ohm here and 6.5 kilo ohm here, you recover this 1% coupling I was mentioning before. So you need to go beyond the usual circuitry, and this is why we developed this metamaterial in my lab. So the idea is the following. We will use a metamaterial made of Josephson junction. Basically, if you have the usual transmission line, you can demonstrate that the impedance of this guy, the real part, is square root L over C, where L is this inductance and C is this capacitance to ground. So now, if you engineer your transmission line and you make it out of squids, basically you will have a similar expression, but now this is the inductance of the squid. So we are not the first to follow this route. This kind of approach was initiated in David Haviland's group, something like 10 years ago. I think we just managed to put this much further than what was done before. So why using squids? For 3 reasons. First, they are low loss, because we are operating them in the superconducting state. So as I said, we want a control bath, and of course, we don't want any losses within this bath, because if you want to monitor what's going in your bath, but you lose your information before you can even monitor it, basically, you're kind of done. So the second important point in using squids is that you can boost the inductance. So the Josephson or kinetic inductance can be 4 orders of magnitude larger than what you would obtain with a usual piece of metal. So you will be able to boost your impedance by a lot. And finally, as an extra, if you make your metamaterial out of squids and not single junctions, you can also have in situ tunability. So it means that you can rearrange your waveguide in situ in a single experiment. So this was the idea. Now, how do you do this? Basically, you go to the clean room and you spend a significant amount of time in the clean room. It took us maybe close to 2 years to get this technology working, because fabricating these very, very long arrays, this very long object is very difficult, and mainly because of disorder. Because when you are fabricating something side by side, because of variation in the fabrication, you will have disorder, and then all these nice properties I was describing, basically, they will fall down. So basically, these are the 2 characteristics of the disorder we can obtain as of today. You don't need to understand what is this resistance and what is this thing, but the message is that if we characterize the sites one by one, and we plot some kind of histogram, the mean is around 1.2 kilo ohm, and we have a dispersion of 22 ohms. So it means that the site-to-site disorder is something like 2%. So it's really low disorder. So this is a picture of the metamaterial itself, the waveguide itself. There is no qubit now. So this is really a chip. So it's 5 millimeter wide and 1 centimeter long. And then if you zoom in and you use an SEM microscope, this is what you will observe. So you have a very, very long array of squids. In this case, it's made of 5,000 cells. Just to give you an idea of the difficulty, the smallest dimension here is 200 nanometers. So this will here. So basically, it is 200 nanometer, and you want to keep this as constant as possible over a centimeter length. So you have something like 4 orders of magnitude to master. So of course, there were a lot of troubles, but as I said, we are lucky in Grenoble. We have a very nice clean room equipments. So we could fabricate this. Now the question is, how do you measure that? Basically, we want to be in the quantum regime. So we want to be at a temperature which is low enough so that KBT is much smaller than all the relevant frequencies. And to do so, we are using our favorite instrument, which is a dilution refrigerator, and then everything we are measuring is at 20 millik. So the sample is here, and then we have various filters and attenuators. The sample is here, and then we have amplifiers to amplify back the signal and measure it at room temperature. So let's come to the real measurements. It's a very, very easy measurement at first. So we are, maybe, let me show you. So you see here, the metamaterial is between these 2 rectangles. You don't see it. You just see this rectangle, and this is where we're going to attach probe. So 1 probe on the left and 1 probe on the right. And then we're going to measure the transmission between this object. Really like a microwave transmission measurement, or similar to an optical transmission measurement. The point is, between this probe here and the metamaterial, there is a difference of impedance. So it is very much similar to some kind of semi-transparent mirror. And you have the same on the edge here. So you have another transparent mirror. So you see that you are forming a very long Fabry-Perot cavity. And what we're going to observe are the various modes, are the various possible the various possible modes of this Fabry-Perot cavity. So this is a typical measurement we are making. So this is a transmission. We are using dB because we are microwave working in the microwave domain, but it doesn't really matter. So it's just transmission, and this is frequency, and you see a very nice forest of peaks, and these peaks are all the various modes of the Fabry-Perot cavity. Just to give you characteristic number, the internal quality factor is 10 to the 4, so it means that the photons in this metamaterial will not die before they can escape the cavity, and we can measure them. Because the rate at which they leave the cavity is inversely proportional to this one, which is 10 to the 2. So we have 2 orders of magnitude difference between the internal dissipation and the external dissipation, which is basically what we measure. So you can go further. Of course, you want to characterize the band dispersion of your metamaterial. So this is frequency versus K vector. So to do so, it's very simple. We just measure the position of each peak and report the position of each peak on the graph. Very, very simple. So it's a bit similar to the dispersion relation we've seen in other talks during the week. It's just that here we are dealing with photons, with bosons. So basically, at the beginning, it's linear. So it's omega equal c times k, very simple. And then it bends because there are some other effects due to additional capacitances in the circuit. The point is, we can develop a very simple model based of this electrical model, and then solve this, and we obtain this blue curve. It allows us to infer all the parameters of our circuit. So we can know what is CG, CJ, and LJ, and these names correspond to this graphic. So we can basically in situ characterize our metamaterial, so we can really understand what's going on. And for this typical case, we obtain a characteristic impedance, which is 3.5 kilo ohm. So it's really close to this quantum of resistance. If you prefer optics wording, it translates into a refractive index of 50, which means that the light is very, very slow. So it's also going to enhance the interaction with our two-level system. Okay, so now, I don't know how much time do I have. Okay, thanks. So now let me show you what's happening when we couple a quantum emitter to this photonic waveguide or metamaterial. So, of course, as you've heard also previously during the week, we love to use the Transmon qubit because it is easy to fabricate, it's highly coherent. So basically, this is the workhorse of many groups now. So to do this experiment, we thought about the most simple configuration. We have the metamaterial on the right, and we couple this Transmon, this qubit to the left. And then we make a similar experiment than before, which is a transmission experiment. And this is how does the sample look like. So there are 2 parts. On the left, you see the qubit, the Transmon. And on the right, this long, faint line here is the metamaterial. These 2 here and there interdigital capacitors, there are these coupling capacitors here. So basically, you see that we are trying to increase the coupling as much as possible between the Transmon qubit here and the array there. An important point is that there is a loop in the Josephson junction of the Transmon, so we can in situ tune the frequency of our qubit. But also, our metamaterial is made of many, many squids, so each site is also in situ tunable. So we have 2 knobs, we can tune one or the other, depending on what we want to do. So again, the simplest experiment possible, we make a transmission measurement through this system, and this is what we observe. So transmission versus frequency, and you see another forest of peaks. But if you remember the previous plot, there are 2 different features. First, you see that the width of the peak is not constant. This one is much wider than the one on the edges. And you have a background here. So it seems that indeed the fact that the qubit is in there is doing something. Of course, now we have various knobs, so the first thing as an experimentalist you want to do is to apply flux to your qubit and see how this qubit is interacting back and forth with your metamaterial. So this is a 2D plot. So basically each slice here correspond to the graph you've just seen, but at different magnetic flux. So you have frequency here, flux threading the qubit loop there, and the color codes correspond to transmissions. Basically, white is low transmission, blue is high transmission. And you see that you have some kind of parallel lines, and then you have some periodic modulation on top of that, and obviously the periodic modulation is coming from the qubit. You can zoom in a bit more, and you see that still the spectroscopy remains super clean, and now we have all this line going around. It seems that there are some kind of anti-crossings, but when it's not really well defined, and you see that when the qubit arrives in the measurement windows, it seems it's interacting with more than one mode at once. Of course, the question we ask ourselves is how to understand this thing, because we might want to fit that, for example. We might want to put a theory line on each of these spectroscopic lines. But the problem is that actually we couldn't do it. And it's not because we don't have a supercomputer whatsoever. It's just that the size of the Hilbert space associated to this system starts to be really significant. Because you see, we have one qubit, so 2 degrees of freedom, that's fine. And then we have all these oscillators. So in principle, the waveguide is made out of 5,000 sites. So maybe you have as many as 5,000 oscillators. But in reality, not all of them are coupling to the qubit. So maybe you can say, okay, I have 10 oscillators at a higher frequency and 10 oscillators at a lower frequency compared to the qubit. So I have to account for 20 oscillators coupled to this qubit. But the coupling is really strong, and it's nonlinear. As Ash would say, it's more than just a bunch of coupled oscillators. So you cannot just use the usual classical way of diagonalizing your system. And since these harmonic oscillators are much than a two-level system, using brute force diagonalization of this 20 mode coupled to one qubit is basically impossible to handle, or at least we couldn't do it. So we used a much more simpler approach, which is more experimentally oriented. So we thought, okay, the idea is to see how does the qubit reshuffle the modes of the bath. So we said, we know we can tune the qubit out of the measurement window. And this is the meaning of this horizontal line. Because when the qubit is out of the measurement window, basically, we have the bare mode of the cavity. So these are the horizontal lines you have here and there. And then we tune the cavity in and out of the measurement window, and we look at how different the spectrum is. And this is the meaning of these purple points. And you see that when you're here, for example, at zero flux, you have many modes, many dots, many purple dots, which are not aligned with the orange line. So it means that the qubit is indeed interacting with many modes at once. Then there is a much simpler way to plot this. It is what we call the degeneracy lifting spectrum, which is very simple. You are just plotting the difference between the orange line and the purple dots. So basically, you are just looking at how different it is when I have my qubit and when I don't have it. And it looks like this. So this is degeneracy lifting versus hybridized frequency, or if you want, just frequency. And you see this very nice step. Of course, the data are the dots, and the line here is the theory, and I will come back to that. But before coming to the theory description, I would like to mention two important features of this graph. Basically, the first thing you want to look at are these two horizontal lines. Basically, when the data points are reaching this line, it means that the difference between bare and hybridized is zero. So basically, the modes which are on this horizontal line here or there, they are not coupled to the system. But you see that there are many points between these two lines. And this is the way we use, the very simple experimental way we use to quantify how many modes are hybridizing with our qubit or how many modes are coupled to the qubit. And we could have as many as 10 modes for this first experiment. So we are really happy about that. It means that it's not yet a super many body system. It's a few body system, but still 10 starts to be really significant and not so easy to track theoretically. The second feature, which is important, is that you can measure, you know, it's like a step function. So you somehow can measure the width of this step function. And this step function width is basically the strength of the coupling. So now you can infer this ratio, gamma over omega 0,1, and it happens to be 15%, 1.5 in this experiment. So it means that indeed we are entering this multimode ultra-strong coupling regime. So as I said, doing something a bit smarter than just brute force diagonalization, thanks to our theory friends, we could work out some theoretical description. So for specialists, we used a self-consistent harmonic approximation. So basically to account for the self-consistent normalization due to the qubit on the bath. And then we could explain our data pretty nicely. So this plot is similar to the one before, but at various magnetic flux. So you see that there is a very good agreement between theory and experiment on a very broad range of magnetic flux. And I must say that there is only one fitting parameter for all these curves because we can characterize everything in situ. And this fitting parameter is the Josephson energy of the qubit, because this one, we have nowhere to measure it in situ. So we are pretty happy to see that with only this little fitting parameter, we could explain pretty much all the physics in this complex system. All right, so to conclude, I think my time is almost over. So I've shown you we've developed a high impedance Josephson junction metamaterial. It's a bit like some kind of photonic waveguide, if you prefer. And we could couple it very strongly to a qubit. And we could measure as many as 10 hybridized modes between the qubit and the bath. So, of course, now what's next? What are the perspectives of this architecture? One, I think, very interesting question is to understand what will happen if we try to scatter light on such a many-body system. Because if you have one single atom or one single harmonic oscillators, these things are pretty well known. But when you have this many-body system, what will happen? Will you observe the same photon at the input and at the output? Will you have some frequency conversion? So we are now trying to develop the theory on that. And again, if you want more insights, I encourage you to go and discuss with Nicolas in his poster. Another interesting things, and we've seen very interesting experiment along this line by Jacqueline, would be to shape the bath, because here the cells of our crystals, they are all the same. So it gives us a linear dispersion, but we could imagine having different cells with different shape, and then we could have various bands, maybe edge states or whatsoever, and couple them to our qubits. And also maybe on a more perspective side, we could dream about studying other models. Basically, instead of using a Transmon qubit, we could use other types of non-linearity and go towards the Kondo or the sign-Gondon model. So with this, I would like to thank again all the people involved in this work, and I would like to thank you for your attention.
You had these qualitative features that you pointed out in the transmission spectrum, that it rises in transmission and the peaks are broader.
Yep.
And did I miss, do you have a qualitative explanation for all those features?
We do, and you didn't miss it because I didn't give it. Okay. So my naive experimentalist picture is that you have the qubit here. We are sending light from the left to the right. So basically, what you see is something which is a convolution between the qubit spectrum and the array spectrum. And if you want, the qubit is like a big, wide Laurentian. So basically, this, if you want, is also, the width of this thing is related to the gamma of the qubit.
So the gamma of the qubit is very large.
Yeah, so it's another proof that the gamma of the qubit is very large. In a similar way, since these peaks, they are standing on the top of the Laurentian, they are broader than the one on the edge. So it's another indirect proof that the coupling is ultra strong.
So when emphasizing the ultra-strong coupling regime, the ratio gamma over omega, omega is the frequency of the fundamental mode, or the free spectral range. Is this correct?
The fundamental mode, the 0-1 transition of the qubit.
Of the qubit?
Yes.
Okay. Do you think that this ultra-strong coupling is really necessary to see this physics? And,
It depends
I mean,
on
these
what...
counter-rotating terms that you would otherwise neglect, do they play any role in seeing this?
Yeah, I think basically, yeah, I didn't enter the full microscopic description of this coupling, but basically this is what I somehow meant when I said, okay, we tried to extract the spectrum of this. So basically we need to diagonalize the full Hamiltonian, and since G is on the order, G per mode, the coupling per mode is on the order of the frequency of the qubit, you cannot do the rotating wave approximation anymore. So then you have to really diagonalize through the full thing, and this is why it is so difficult. And so this is the technical, I would say, detail. Now, if you want some physical insight, it's been demonstrated by your theorist collaborator that if you want entanglement to build up in your bath, you need these counter-rotating terms. So if you don't have them, you won't have any entanglement in your bath.
Right, because in principle, it would look like you can just, if you were able to achieve a smaller free spectral range, you could decrease the coupling as well and still have multimode coupling. But maybe some of the physics you're after.
Yeah, I mean, if you do so, and this was done by this, I mean, these ideas are pursued by other group, you will indeed have one qubit coupled to many modes, but for each mode, you can treat the coupling as not a perturbation, but you can do the rotative approximation for each mode. So you won't have this counter-rotating terms effect, you won't have the entanglement building up in the bath directly from the coupling.
Thanks.
It's interesting physics, but it's different. Yeah. And yeah, we did. And yeah, I think I don't have the slide here, but basically what you see, you can measure similar spectrum at n number of photons small and n number of photons large. And basically what you see is that you are completely saturating your qubit, so you recover the spectrum of the bare modes. So basically this peak here disappears because it's the one which is most qubit-like, and you recover the bare modes. This is another check we did. No, it's a very good question. You want to call it many-body physics if basically the coupling is so big that all these photonic modes are interacting together via the qubit. So basically, you have a nonlinear coupling between each mode and the qubit. And so if you make this coupling large enough, even though you don't have any interaction between the modes, the photonic mode at the beginning, via the qubit, they might all become entangled at the end. So if you want, you have some kind of huge photonic entangled state if you can crack up the coupling. If you want, we like to see the qubit just as a mediator. It mediates the... Yeah, so, and then you can demonstrate, I mean, if you're interested in the photonic part, you can show that if you crank up this coupling, the photonic wave function contains many photons at various frequencies, and they are all rearranged in a coherent way, which was demonstrated to be a CAT state, a multimode, many frequency CAT state.
Is the shift in the peaks, I mean, that by how much do the peaks shift? I mean,
you can see it on this picture. You mean with and without the qubit?
Without the qubit, yeah. So,
I mean, basically, this is what we plot here. You see, this is the difference between. This is the shift you want to know. We are just normalizing it by something. So basically, the shift can be as large as the free spectral range. You see it here. You see this peak here. It is the position. This orange line is the position where the qubit is not here, and it is repelled very far away, almost as close up to the next level.
Another question. So if without the qubit, I guess if you like transmission left to right and right to left would be the same, right? Without the qubit.
And with the qubit as well.
It changes.
No.
It doesn't change?
No, I mean, you don't have any magnetic field. I mean, you have a magnetic field, but it's a static one, so there is no way you can break time reversal symmetry here. we are probing from the left to the right because for experimental reasons. But if I would probe from the right to the left, that would be, should observe the same. I mean, you need to break time reversal symmetry